Okay, good morning, students. Today we will start, before starting with single sideband suppressed carrier modulation, uh, I will just brief you about double sideband suppressed carrier, double sideband, double sideband suppressed carrier, right? Okay, so double sideband suppressed carrier, what were the disadvantages associated with this double sideband full carrier? I will just note down here. We have double sideband full carrier transmission. In this, there were certain disadvantages. That's the reason we switched to double sideband suppressed carrier. Uh, I can say it's not advisable. Why? Because there are certain disadvantages. First one is carrier does not carrier does not contain any information that you people know. That carrier does not contain any information. So that means uh, carrier transmission is just a wastage of power resources. That's it. So you should try to avoid carrying this carrier because it's just a carrier. It does not contain any information as such. Also, at MA, that means modulation index equal to 1. That means when modulation is 100%, two-thirds of total power that we have already done with these expressions is contained in carrier power. So these are the two biggest, which is total wastage, obviously, and this is total wastage, you can say. And so, in order to avoid this, carrier is suppressed. So, in order to avoid this, in order to avoid in order to avoid this, carrier is suppressed. Carrier is suppressed. So, but both the upper side band and lower side bands are transmitted. Carrier is suppressed, but in the spectrum, you already know that you have one is upper side band, this one, and this one is your lower side band. If I can consider this as a spectrum of some signal, information signal. So both the side bands are transmitted, but carrier is suppressed. And this type of modulation is called as double sideband suppressed carrier modulation that we have already discussed in detail, right? That means you don't transmit carrier power is saved here, but you transmit message signal with both the bands, upper sideband and lower sideband. Now, how can you generate this? So generation of double sideband suppressed carrier. First one, which we have already studied, that's balanced modulator. Second one is a ring modulator. These are the two modulators by which you can generate double sideband suppressed carrier. Just a brief introduction because for going for the single sideband suppressed carrier. So balanced modulator, first one. So you have, this is your message signal, M of P. This is your you can say this is your product modulator here, and this is carrier C of T. And this is equal to AC cos of omega CT, and this is your message signal. You can say this. Then at the output, you get Y of T is equal to X DSB suppressed carrier, and that is equal to AC MT cos of omega CT. That means now you don't have any separate carrier, you have the carrier with this message signal. That means you don't have any separate carrier, and in this way you can say that you have suppressed the carrier transmission and hence saved the power as well as spectrum, right? Anybody having any query, please tell me.
No, sir.
Okay, then you have spectrum of double sideband suppressed carrier signal. How its spectrum will look like, because you already know the spectrum of double sideband full carrier. Then now try to visualize the spectrum of double sideband suppressed carrier. Its spectrum will look like this. So suppose this is your message signal spectrum of a message signal. You are assuming this triangular shape, this, and this is your omega. Let this be the highest component be omega m. This is 0. This will be minus omega m, and this value will be m of 0, right? And this is your m of omega, right?
Yes, sir.
Okay. Then if you will try to draw the spectrum of double sideband suppressed carrier, double sideband suppressed carrier, double sideband suppressed carrier, then now how this will look like? Okay, spectrum will be like this. There will not be any spike at this, because you know that in case of double sideband full carrier, there was one spike here. There will not be any spike. That's called a delta signal. There will not be any spike here. So you have this is omega, and this one will be your omega C. This one will be omega C plus omega M, and this will be omega C minus omega M, right? And this component will be your AC by 2. Similarly, here you have this is minus omega C. This is minus omega C minus omega M, like this, and this is minus omega C plus omega M, this point, and this value here, this will be your AC by 2, and this is just your X DSB suppressed carrier omega. Are you getting my point? What's missing? If you will compare this with double side band full carrier, then your spectrum was like this. This is one, this is one. There was one spike here. That was the carrier signal. So there is no carrier signal here. That means you can relate this, that you have managed to suppress the carrier signal. But what about the transmission bandwidth? It will remain the same. Transmission bandwidth means bandwidth, total bandwidth from here to here. That's your bandwidth. Negative just about the sake of symmetry. There is no negative frequency. You must remember this. So transmission bandwidth is upper value, that's this value minus this lower value of the this, because range of frequencies that will determine your bandwidth. So you can say bandwidth will be omega C plus omega M minus omega C minus omega M, and in general, after solving this, you will get twice omega M. So transmission bandwidth or bandwidth is equal to 2 times the maximum frequency of the message signal. You just remember this. Then, anybody having any doubt, please tell me. Then we will proceed.
No, sir.
Okay. So then this we have already studied. I was just brushing up the things. So second one by which you can generate this is ring modulator. Ring modulator. ring modulator, in this case, it's also called RM. It's ring modulator. Before analyzing the situation, how you can determine the double sideband suppressed carrier, I will just draw the figure for the same, and the figure for the same is the circuit diagram rather of this circuit diagram. Okay, you can draw with me. So this is your double sideband suppressed carrier output. This is your M of D. This is D1, D2. This is your transform, obviously. And there will be, this will be plus. This is your second transform. Now, in this case, from the circuit diagram, you can analyze that for positive half cycle of C of T, there is M of T and there will be positive cycle of M of T. And for the positive cycle of M of T, what will happen? Not C of T, sorry, because this is message signal, there will be some carrier, what you will determine. And for the positive half cycle of C of T, both the diodes will be on. Both the diodes D1 and D2 will be on. And for the negative half cycle, other two diodes will be on. Because this is not the full diagram which I have shown here. This diagram is actually this. I will make the full diagram before you will realize what is happening. Okay. This is D4. Similarly, here this is D3. Then this point here, this one is your C of D. And this will go to this. Are you getting me now? How this look like? This is the circuit diagram of ring modulator. Saib, are you getting me? Circuit diagram of ring modulator.
Yes, sir.
Okay, this is the diagram final. Now we will analyze the diagram. Now first point is for positive half cycle of C of T, diode D1 and D2 is on. For the positive half cycle, that means this is considered as positive, and positive half cycle of this positive, negative, then this is positive, negative. You can say this one is positive, negative, and because of this is positive and this is negative, similarly this will be positive and negative. Which one is on? This is positive and this is negative, so D1 is on because this is forward biased, right? If this positive comes here and this is forward biased because of this reason. Now second one, you can say D2. Which one is D2? This one. So this one, since this is positive, and this one will be also on. D1 and D2 is on for this whenever you have this as positive, because you are concerned like this. This is positive, this is negative, so this is negative here, this is negative here, and this one is positive here, but it's showing the reverse biased. Wait a minute. Okay, maybe you will understand much better from this graph. Suppose this is your message signal. This is positive half cycle and this is negative half cycle, and this is your M of t. Then this one will be your carrier signal, and this is your carrier signal. Dash dash dash. This is t, and this is c of t. Right till now? Okay. Now we will see here what my output will be look. Suppose in the first half, this is DSB output, obviously, DSB output. In the first half, two diodes are conducting. That means in this half, whenever this is positive, we have two diodes will be conducting. That means D1 and D2. You try to understand in this half, this is positive half. In this half, D1 and D2 will be conducting, and in this half, D3 and D4 will be conducting. Similarly, in this, D1 and D2 will be conducting, and D3 and D4 will be conducting in this. So alternatively, because this is an alternate cycle, so conduction will be alternate. So how can you draw the diagram of this? Okay, first half, it will be like this. After this, then this one. Wait, because it will be like this also. So ये यहाँ से यहाँ तक आएगा, then this will be like this. Then little bit conduction, then this will like this, then little bit conduction, then similarly this, then little bit conduction, then this, little bit conduction, then this, little bit conduction, then this one, little bit conduction, then this, then this. Similarly, for the negative half, it will be like this. Are you getting me what I am saying? How it will look like?
Yes.
Something like that it will look like. Now I will tell you, I will draw this with the red pen so that you will understand. In this period, in this one, D1 and D2 are conducting. Two diodes are conducting. And in this one, in this case, because this negative period, this is negative, because you can say D3 and D4 are conducting, and hence this shape. And this is the shape of double sideband output, how it will look like. Double sideband suppressed carrier output. I hope you will go through this and then understand this. If you people will be having any doubt, do tell me, right?
Yes, sir.
Okay, so we continue with this. Ultimately, you can say if instead of carrier being sinusoidal. If you have a carrier other than sinusoidal, how you'll get the output? Suppose I will assume this is for the same double sideband suppressed carrier using a ring modulator using RM. Suppose you have your this is your message signal T M of T, and let this be your s- this be your carrier signal. Carrier signal is this is 1 volt, and this is a perfectly symmetric carrier signal. This minus 1 volt, right? This is your T. If you will, how you will get the output? I will just draw the output. This. So output in this case will be like this. Similarly, for this will be. Are you getting me? So this solid figure is the output, and this is your double sideband suppressed carrier, and its advantage already listed in the beginning. So you can say if this is the final output and ring modulator, you can say that ring modulator, which gives you the double sideband suppressed carrier, just performs the multiplication. Ring modulator, you can say simply performance, you can say it's simply performance multiplication, multiplication of your M of t message signal with C of t, and resultant will be this. This one will be the result. Right? Any doubts?
No, sir.
No, sir.
Okay. So finally, uh, we have to see what your single sideband suppressed carrier is. What is the reason why we are going for this? So single sideband suppressed carrier modulation. So far as the transmission of information is concerned, since in case of double sideband suppressed carrier, we suppress the carrier, but still there are two sidebands which carry the information like this. I will just draw the background here. We have this, there's no carrier obviously, but there are still two bands. One is upper sideband, another one is lower sideband. And upper side and band and lower side, they transmit the similar information. So there is no need for the transmission of the both bands. We can we can transmit only single side band, and that's necessary for the information. There is no need for duplication of the information or redundancy. So if carrier and one side band are suppressed, we have only 10 minutes, so I will just try to wind up this. So if carrier as well as one side band are suppressed at the transmitter, no information will be lost, because ultimately we are dealing with information. No information will be lost, but much more power will be saved. More power will be saved. So the technique in which you transmit only single side band, you transmit only single side band. That means this is a transmission with suppressed suppressed carrier with single band. Still no information will be lost. Because of this, no information will be lost, but power will be saved. Power will be saved. Another important point, advantage, transmission bandwidth will be reduced. Transmission bandwidth will be reduced. And power and transmission band, they are very important resources, and bandwidth is not available in abundance. So that's obviously one of the best advantage for this. So I will just little bit go for the generation, how you can generate the single side band generation. Then we will discuss this in this tomorrow, inshallah. So generation of single side band suppressed carrier. So one of the methods is just you have M of T, pass this through a product modulator, modulator. After this, you will get obviously double sideband suppressed carrier. This is your carrier C of T, and that is equal to AC cos of 2i pi FCT. And ultimately, you will get you here double sideband suppressed carrier. Then you pass this through a band pass filter. Band pass filter. After passing through the band pass filter, you will get your output as SSB modulated wave, SSB modulated wave or modulated signal. So this is one of the methods of generation. There's also another method that's called two-stage SSB modulator that we will discuss tomorrow. Any queries, questions, please tell me.
No, sir.
Okay, thank
No,
you.